Welcome. After thousands of trials, 4 months of continuous effort, and way too many hours of unpaid labor, I'm finally bringing you the tool and die design for manufacturing the legendary .45 ACP cartridge case. And when I say labor, I mean it. My poor computer has been running finite element simulations like it's training for a marathon. The software? Let's just say it crashes more than I do after pulling an all-nighter. But hey, who needs sleep when you've got brass to simulate? Now, the process took 16 stages in total. 1 cupping stage, 6 drawing stages where the brass gets stretched thinner and thinner, 3 trimming stages to cut off extra length so we end up with the precise 22.81 millimeter final case length. Then, the 2 head forming stages, including the primer pocket stage. And because no one on the internet wanted to share the base thickness dimension with me, I had to calculate it myself, 4.10 millimeters, all unpaid, of course. Apparently, sticking around in engineering projects is harder when nobody's paying you. Finally, I simulated the machining stages, carving the extractor groove with a custom tool profile, drilling and flattening the primer pocket, and trimming off the last scraps of brass. By the end, the simulation gave me a finished .45 ACP case, and hopefully, my computer forgave me for the torture. So yeah, this whole project wasn't just about cartridges. It was about designing the dies and tools, validating them with simulation, and proving that with enough unpaid hours and coffee, even a crashing computer can help you make history. And remember, switching to your secondary is faster than reloading your primary, but only if your secondary has the stopping power of a .45 ACP. All right, enough talking. Let's get to the video. All right, let's kick things off with the very first step, the cupping operation. Now this is where the magic begins. We start with a flat brass disc, 28 millimeters in diameter, 5 millimeters thick. Before anything else, it takes a dip in lubrication, because trust me, you don't want to run this stage dry. Lubrication here isn't just optional. It's the difference between a clean, smooth cup and a mangled disaster. It reduces friction, prevents tearing, and keeps our tools from crying themselves to sleep at night. Once the disc is ready, it's placed concave side up. On the downstroke of the press, the punch forces the disc through the die and stripper, forming it into a cup shape. On the upstroke, the stripper neatly pulls the cup off the punch, and then the cup slides down an inclined chute like it's on a brass playground, safely out of the press. Simple in theory, critical in practice. Here's what the simulation gave me. Final cup radius, 10.49 millimeters, bottom thickness, 4.3640 millimeters, total height achieved, 16.48 millimeters, punch speed was set at 3 millimeters per second, maximum load required, 5.2 tons, and the whole cycle wrapped up in about 5.5 seconds. Not bad for step 1, right? The finite element analysis gave me solid numbers to work with, and we already see the case beginning to take shape. One more note here, grain size. After annealing, we're aiming for between 0.020 and 0.10 millimeters under 100x magnification. That's important to maintain strength while keeping the brass workable for the following drawing stages. So yeah, stage 1 may look simple, it's just making a cup, but it's the foundation of everything that follows. Get this wrong, and the rest of the process doesn't stand a chance. Stage 2, first draw operation. Now, let's move on to the first draw operation. Here, the cup we produced in the cupping stage is stretched further. As always, the cups are dipped in a lubricating solution before being placed in the press. Lubrication is critical. It reduces friction, prevents tearing, protects the punch and die, and ensures a smooth, precise surface on the brass. Now, watch the FEA screen capture on your video. This animation shows exactly how the material flows as the punch moves at 3 millimeters per second. Notice how the brass deforms gradually and evenly inside the die. From the simulation, here's what we achieved. Outer radius, 9.004 millimeters. Bottom thickness, 4.364 millimeters. Total height, 27.27 millimeters. Maximum load 5.25 tons. Estimated cycle time 9 seconds. After the draw, the cup undergoes annealing and pickling. Check the FEA animation again. This is how the brass is prepared for the next stage. Our target grain size after annealing is between 0.020 and 0.10 millimeters at 100x magnification, ensuring the material is soft enough for the following draws but still strong. So, Stage 2 is all about carefully stretching the brass while maintaining precision. Keep your eyes on the FEA screen recording. It shows exactly how the material behaves under load. And next to it, you can see the measurements we're aiming for. Step by step, our cartridge case is starting to take shape. Stage 3, second draw operation. All right, let's move on to Stage 3, the second draw operation. This is where the cup really starts to elongate. As always, we begin by dipping the cup in lubricating solution. This is crucial. Lubrication reduces friction, prevents tearing, and keeps both the punch and die safe while producing a smooth brass surface. Then the cup is placed in the dial feed of the press, ready for the punch to do its work. Now watch the FEA screen capture on your video. The punch moves steadily at 3 millimeters per second, drawing the cup into a longer, narrower shape. See how the brass flows smoothly along the die? That's the beauty of simulation. You can observe strain and deformation in real time without risking actual material. From the analysis, here's what we achieved. Outer radius 7.925 millimeters. Bottom thickness 4.352 millimeters. Total height 43.76 millimeters. Maximum load 3.5 tons. Estimated cycle time 14.5 seconds. After this draw, the cup undergoes annealing and pickling to restore ductility and refine the grain structure. Our target grain size after annealing remains between 0.020 and 0.100 millimeters at 100x magnification, keeping the brass soft enough for the next stage. Even though we'll trim the cup briefly before the next draw, that's a simple step, so we won't show it in the video. For now, keep your focus on the FEA animation. Watch how the material stretches and flows precisely into shape. Stage 3 is all about controlled elongation, maintaining dimensional accuracy, and preparing the brass for the next critical draw. Now we're at Stage 4, the third draw, and here's where you can really see how the process evolves. As always, our cup gets a dip in lubricating solution before being placed in the press. Lubrication is key at every stage. Without it, friction could tear the brass, damage the punch, and ruin the smooth surface we've been carefully forming. Now, look at the FEA screen capture on your video. Watch how the cup continues to elongate and the diameter starts shrinking. Compare it to the previous draws. Stage 1 required 5.2 tons, Stage 2, 3.5 tons, and now, in this third draw, it's only 2.64 tons. So, the load required is clearly decreasing with each draw, showing how the brass becomes more compliant as it elongates and the strain distributes. Now for the dimensions. Outer diameter has decreased to 7.198 millimeters. Total height is 31.84 millimeters. And here's the cool part. The bottom thickness has stayed almost constant at 4.394 millimeters. That's exactly what we want. The base is stable, keeping the cartridge strong, while the walls and diameter continue to adjust. After this draw, the cup will undergo annealing and pickling, keeping the grain size between 0.020 and 0.10 millimeters at 100x magnification. This restores ductility for the next stage and ensures uniform deformation. There's also a quick trim step to bring the cup down to 20 millimeters for better performance before moving to the fourth draw, but we won't show it in the video since it's straightforward. So, if you're watching the FEA animation, notice how the material flows more smoothly than in the earlier draws, the stress is more evenly distributed, and the base remains solid. Stage 3 really highlights how careful control lets the brass evolve without compromising strength, one step closer to our final .45 ACP case. Stage 5, fourth draw operation. Here we are at stage 5, the fourth draw. The cup is really starting to take the shape of our final cartridge case. As usual, the cup is dipped in lubricating solution before being loaded into the press. Lubrication is key at every stage. Without it, friction could tear the brass, damage the punch, and ruin the smooth surface we've been carefully forming. Now, look at the FEA screen capture on your video. Watch how the cup continues to elongate and the diameter decreases. Comparing it to the previous draws, Stage 1 required 5.2 tons, Stage 2, 3.5 tons, Stage 3, 2.64 tons, and now in Stage 4, we only need 2.24 tons. The trend is clear. As the brass stretches and becomes more compliant, the load required keeps decreasing. At the same time, the outer diameter shrinks to 6.659 millimeters, the height is 30.93 millimeters, yet the bottom thickness stays solid at 4.364 millimeters, just where we want it. This stability at the base ensures strength while the walls and diameter continue to adjust. After this draw, the cup will undergo annealing and pickling to restore ductility and refine the grain structure. Target grain size remains between 0.020 and 0.10 millimeters at 100x magnification. This restores ductility for the next stage and ensures uniform deformation. There's also a quick trim step to bring the cup down to 20 millimeters for better performance before moving to the fourth draw, but we won't show it in the video since it's straightforward. So, if you're watching the FEA animation, notice how the material flows more smoothly than in earlier draws, the stress is more evenly distributed, and the base remains solid. Stage 3 really highlights how careful control lets the brass evolve without compromising strength. One step closer to our final .45 ACP case. Stage 6, fifth draw operation. Welcome to Stage 6, the fifth draw operation. At this stage, we've set the punch speed to 3 millimeters per second, and the cup is stretched taller and slimmer once again. The FEA animation shows the material flow beautifully. Smooth walls, stable base, and no tearing thanks to proper lubrication. Now for the results. Final height, 54.15 millimeters. Outer diameter, 6.286 millimeters. Bottom thickness, 4.364 millimeters. Cycle time, 18 seconds. Load required, just 1.84 tons. Notice how the punch load continues to decrease with each stage, from over 5 tons in the very beginning to under 2 tons here. That's the brass working hard, getting thinner and longer, but the base thickness remains steady to ensure strength at the bottom. After this draw, we trim the case down to 25 millimeters before annealing, which helps control the material for the next stage. Simple trimming, nothing fancy, but it keeps our process efficient. So, as you watch the FEA simulation, remember, every draw gets us closer to the final cartridge dimensions, with less load, smaller diameters, and a base that holds strong. Stage 7, sixth draw operation. Now we're moving into Stage 7, the sixth draw operation. At this stage, the punch still runs at a steady 3 millimeters per second, but the brass has reached the final stretch of its deep drawing journey. Look closely at the FEA animation. The walls extend taller and slimmer, while the base remains solid and intact. Here are the results of this draw. Final height, 43.22 millimeters. Outer diameter, 6.052 millimeters. Bottom thickness, 4.435 millimeters. Cycle time, 14.5 seconds. Punch load required, only 1.37 tons. If you compare this with the earlier stages, the pattern is clear. Every draw requires less punch load, the diameter reduces further, and the base thickness stays strong, slightly even thicker here to prepare for head forming. One critical note. After this stage, only the base is annealed, not the entire case. This local annealing ensures the grain structure at the base is refined and soft enough for the upcoming head and primer pocket forming operations, while preserving the strength of the neck and walls. So, as the FEA simulation rolls, keep an eye on how little force is needed now compared to those early heavy tonnage draws. Brass may be stubborn, but with every pass, we're bending it closer to perfection. Primer Head Forming Operation 1. Now we're moving into Head Forming Operation 1, a critical stage for shaping the base of our cartridge. For this step, we only anneal the lower base of the cup. This softens the material where the head will be formed while leaving the rest of the cup strong. Then we set the workpiece upside down in the press. Watch the FEA animation closely. The head-forming tool descends, shaping the head and increasing the outer diameter to create space for the extractor groove. Notice how the material flows smoothly into the new profile. The annealed base allows for deformation without cracking. Primer Head Pocket Operation. Now we're at the primer head pocket operation, which is performed in much the same way as head forming operation 1. For this step, we only anneal the base of the cartridge case. This softens the material in the critical area where the primer pocket will be formed, while preserving the work already done on the neck and walls of the case. The workpiece is set upside down in the dial, ready for the tool to do its job. Check the FEA animation on your screen. The primer pocket forming tool descends, carefully shaping the pocket and slightly increasing the outer diameter to accommodate the extractor groove. Watch how the annealed base allows smooth deformation, no cracking, just controlled material flow. Remember, after every pass up to the 6th draw, the whole cup must be annealed to restore ductility. But for the heading and primer pocket operations, only the base is annealed. This improves the grain structure locally and preserves the integrity of the already formed neck and walls. Target grain size of the annealed base is between 0.020 and 0.10 millimeters at 100x magnification, ensuring the material is soft enough to form the pocket without compromising strength. So, as you watch the FEA clip, notice how the base deforms precisely into the primer pocket while the upper case remains stable. This operation sets the stage for a perfectly formed cartridge head ready for the final finishing steps. After annealing, the grain size of the base is between 0.020 and 0.10 millimeters at 100x magnification, ensuring ductility and strength where it's needed most. So, in this operation, we're carefully reinforcing the base and forming the head, setting up the brass perfectly for the extractor groove and the final shaping steps. Keep your eyes on the FEA clip. It shows exactly how the material behaves under controlled deformation. Base turning and extractor groove operations. Next, we move to the machining stages where precision becomes key. First up is the base turning operation. Using a lathe, we remove 0.3 millimeters of material from the base to create a perfectly flat surface. This flat base is essential for cutting the extractor groove accurately later. Then comes the extractor groove turning operation. For this, we use a special custom-designed CBN insert that perfectly matches the profile of the extractor groove. The groove is cut in a single pass, ensuring there are no errors or deviations. The AutoCAD model animation shows how the insert traces the exact profile, giving us a clean and precise groove every time. Watch closely in the animations. The combination of careful turning and custom CBN inserts ensures that the base and extractor groove are perfectly cut, ready for the final stages of the .45 ACP cartridge case. Final trim operation. And finally, we reach the last stage, trimming the cartridge to its final length of 22.81 millimeters. Now, I'm not even going to show you this step. Why? Because it's so ridiculously simple it barely counts. Just a quick trim and boom, the cartridge is the perfect size. Think of it as the cherry on top of all that FEA, drawing, heading, and machining drama we just survived. Easy, precise, and done before you can say, "Why didn't I automate this?" And there you have it, a fully formed, perfectly sized .45 ACP cartridge case, ready for, well, anything you want to pretend it's ready for. Simple, clean, and satisfying. And there you have it, Our brass started as a humble flat disc, and now, thanks to a lot of FEA magic, punches, lathes, and a little bit of caffeine-fueled suffering, it's a proper .45 ACP cartridge case. I've done hundreds of projects in this field. Deep drawing of ammunition cases, bullet forming, copper jacket forming, and I'll tell you something, every single project teaches me something new. That's the real reward of this kind of work. If you want to see more content like this, then smash that like button like your life depends on it. Hit subscribe, share it with your friends, and stick around, because this journey doesn't stop here. But let me leave you with something bigger than just brass, presses, and tool steel. When everything collapses, and history shows us it always does eventually, money won't mean a thing. Paper currency? Worthless. The only things that will hold value are the essentials: ammunition, medicine, clean water, and food. Those four things become the real currency of survival. And the knowledge to produce or preserve them, that's priceless. That's why learning processes like these isn't just some technical hobby, it's a mindset. It's proof that you can start with raw material, shape it, refine it, and create something that lasts. That's confidence. That's independence. That's dangerous, in the best way. So don't just sit back and consume. Learn, build, experiment. Because every skill you add to your arsenal keeps you not just alive, but more than alive. It keeps you capable when others freeze. Thanks for watching. Stay prepared and stay sharp. Share this with someone who needs to hear it. And remember, the future belongs to the ones who know how to make, fix, and fight for what really matters.